Welcome to our webinar out of our regular webinar series, and today's topic would be the introduction of our new STA. Yeah, I can't influence that at the moment. I just noticed that some people were using wrong links, and I don't know how long I shall wait until everybody who wants to join will be here. I'll try to start it as soon as possible because I have other dates afterwards, and I'll be already a little bit late. We will do the same webinar on Thursday, and there will be also a recording on Thursday, so you can have a recording afterwards. So don't worry, you will have a chance to join and will have a chance to watch the recording, and you will also get the presentation if you were registered. Again, sorry for these circumstances. Yeah, so today's topic is clear, and a little bit organization. You will all be muted. You can have, if you have questions, you can chat. You can use the question and answer section. Type some, type some influence there. Yeah, I get the microphone, but it is as it is. It's I think it's the connection, unfortunately. That's also because anything I click here has a massive delay. That's what I'm also noticing, but I cannot influence that. Yeah, it's great that sound is better, but I didn't change anything. That's yeah, so that's all I can do. As said, that's more or less the connection. Or the webinar itself, because there's a massive delay whenever I click something. So I'm sorry for that as well. As said, if there are questions, you can type them into the chat and use the question and answer section afterwards. And please note that it also will be repeated on Thursday, when I hope that the circumstances will be a little bit better. Yeah, I hope you can at least see the screen. So no, I don't have multiple devices connected to my headphones. It's only the one speakers. It's really the connection of the internet. Yeah, regarding myself, so my name is Sebastian Seibt. I'm head of laboratory here at Linseis. I'm a chemist, and I'm working here since 2013. I'm mainly responsible for doing application measurements and introduction of instruments to customers. That's what I do today. And for those who do not know the company, a short introduction of the company. Linseis was founded in 1957 by Dr. Maximilian Linseis in Selb in Germany. That's where our main facilities are located. So we manufacture all instruments here in Germany and distribute them all over the world. We are a family-owned company. We are in the third generation meanwhile. Our owner is Mr. Klaus Linseis, the son of our founder, and his two sons, so the third generation, Mr. Florian Linseis and Dr. Vincent Linseis, are our two CEOs who do the daily business and take care of the company. Our business area is mainly the manufacturing of instruments for thermal analysis, thermal conductivity, and thermoelectrics. And also we offer service measurements in laboratories in the US, in Germany, and in China. Meanwhile, beside our headquarters here in Germany, we have a bigger location in the United States where we have also a big laboratory where we have distributors and technicians. We have a joint venture in China and a joint venture in India where we have our own technicians and our own distributors. And in all the other countries around the globe, we have companies who are representing us. And so you can get access to a Linseis, at least distributor or Linseis consultant anywhere in the world. And in the 4 countries I just mentioned, we have our own people. In all the other countries, we have distributors. Regarding our product range, as I just mentioned, we manufacture the complete range of thermal analyzers. The upper line shows the so-called classical thermal analysis. So it consists of differential scanning calorimetry, thermogravimetry, so DSC and TGA. The combination of these two, the simultaneous thermal analyzer, which is a TGDSC that measures weight change and caloric signal at the same time. We have Dilatometers in many ways for thermal expansion. We have thermomechanical analysis for determination of E modulus or Young's modulus, penetration bending experiments, stress and strain experiments. So that's what I would consider as the classical thermal analysis. In the lower line, you see the product range that goes beyond that. So we have multiple devices for determination of thermal conductivity, thermal diffusivity. Of course, there's the known laser flash technique. We have heat flow meters. However, we also have other techniques like periodic laser heating, thin layer and thin film techniques. We have the so-called transient hot bridge device. We have TIM testers. So there are many ways to determine thermal conductivity depending on sample shape and range of thermal conductivity values of the sample, and also depending on the temperature range. We have analyzers for thermoelectrics for determination of Seebeck coefficient, Hall coefficient, electrical resistivity and conductivity, of course. And all this can also be done at thin layers, at coatings, at complete units like batteries, like little platines, stuff like that. And what makes Linseis a little bit different than the other companies is at least our customization. We have a high and deep degree of customization available. So all these instruments are manufactured by ourselves completely. That means we are quite flexible. We can build them and set them up modular, and we can optimize them according to the customer's needs. That means we can use them at higher pressures, use them at higher temperatures, make custom designs, custom sizes, and adapt a lot of customer wishes into the instrument. That's what's our main strength, and that's what Linseis is mainly known for. Now back to today's topic. Our today's webinar is about the new design of the simultaneous thermal analyzer, the so-called STA. Before I get to the new features, I will show you a brief introduction of the STA. I know that the webinar was held this year already, so you should be aware what a TGDSC does. If not, I will just explain it. As I mentioned before, STA stands for Simultaneous Thermal Analyzer, which means it's a combination of DSC and TGA. You measure the rate change as well as the heat flow of the exactly same identical piece of sample within the instrument, and you get a heat flow reading and a rate change reading. This drawing here on the right side shows the principal setup of the instrument. So you have in the lower part all the electronics, and then there is a housing containing our compensational balance, our thermal balance, which consists of a beamline balance with a counterweight and a sample holder position. You have an electric magnet that more or less can move this beam, and you have position markers that monitor the exact position of the beam of the balance. Once these position markers notice a movement, this magnet will automatically compensate the movement in the one or other direction by increasing or lowering the voltage of the magnetic coil. And out of the voltage increase or decrease of the magnet, you get your direct readout of rate change. At this position here, the sensor rod is connected to the beamline, and at the top edge of the sensor, there are two crucibles, or one crucible. So in case of a DSC, there's two crucibles. So you measure the rate change by the balance that's down here, and you measure the heat flow directly out of the sensor head. The upper part here is a furnace. So the orange parts are the heating elements that can be, so usually they're resistance heaters, so usually they're SiC, MOSI, whatever, and that can be also selected by the customer. They surround this reaction chamber here, and out of this complete setup, you can cover a complete temperature range or broad temperature range, and you get your information about mass change and caloric effects over the complete range. So that's the setup on a scheme, and hopefully you understood what I just explained. Going more into detail, our design is a vertical standing design, as you just saw. That means we put the rod from, so if the system is open, if the furnace opens up, we put the rod from the top side into the setup. It's a plug and play design, so you put your sensor rod in here from the top, so you have a vertical standing balance. That's the design we choose and we mainly manufacture. If you have a look on the market at the competitors and so on, that you will see that there's a horizontal system available, there's a vertical hanging system available, and there's a vertical standing system available. The reason why we do this is it's the most easy sample handling and the most easy sensor exchange you can imagine. It's a little bit more complex setup, but it's the most customer-friendly design. That's why most people build a thermal balance on a way like this. For a TG-only system, the vertical system hanging version is the better choice, or is a good choice, because in the hanging balance, you have the best and most stable TG signal you can get, as the gravity pulls the system into the exact best position all the time, and you do not have to fix the position of your sensor electronically or somehow by your software. As said, in the hanging setup, the gravity is an advantage. In the standing setup, you have to fix this by software, by electronics, which is a little bit more complex. And that's the reason why the pure TG signal in the hanging setup can be a little bit better. However, if it comes to TG-DSC or DSC signal, a hanging system is more complex and it has a quite dangerous gasfall path, because you can get a little bit more convection here. That's why we usually design it standing for TG-DSC anyways. And regarding the horizontal system has the smallest buoyancy effect. That means if you start a measurement, if the temperature in the chamber changes, that has an influence of density of atmosphere, you get a shift of your baseline. And in the horizontal system, this shift is minimized. However, it's a very complex setup. It's a very complex handling. You need 2 rods. You need at least 2 connections to the balance. You need a high purge gas flow. And the sensor also sees some thermal expansion, which changes the angles, and which is also quite complex to set up. That's why almost nobody uses the horizontal system anymore. We did this in the past as well, but just about the geometry, that's why we use a vertical standing design. The output of your signal, what you get if you do a TG-DSC experiment, is something like this. So you get this orange curve here. That is the direct mass change. So usually that shows you the mass loss versus temperature, or the mass loss versus time. Typically, you would transform the absolute values in micrograms or milligrams or whatever you have into percentage, because a percentage can be compared to any other experiment. The absolute value would be dependent on your the amount of sample you have used for the individual experiment. So that's why usually you consider, or you look at, the percentage here. And also the green curve, out of the simultaneous run, you get also the green one. That's the DSC curve that shows you the heat flow, that shows you peaks or effects in the one or the other direction. And the direction indicates if something is endothermic or exothermic. So if energy is consumed or energy is released by the sample, it shows you the exact temperature or time when this effect is happening. And the area beyond the peak gives you the exact amount of energy that is released or consumed in joule per gram. So it's referred to the mass that you're using. The blue curve up here that's shown here is just the derivative of the orange one. So in case of a multi-step mass loss, sometimes it's useful to have a look at the derivative automatically, because that helps to differ some effects from each other. So if this is a 2-step effect or 1-step effect, sometimes it's not so easy to see. So in that case, it's a good idea to have a look at the derivative to see there are 2 maxima. That means there's 2 mass loss steps that are quite close to each other. You also see that there's 2 peaks on the DSC line, which also indicates it's 2 effects. So this is the typical outcome of such an experiment. Now, coming to our complete STA range. With our STA program, we cover a temperature range from -196 centigrades, so from liquid nitrogen temperature, up to 2400 centigrades, which is a graphite or tungsten furnace range. We have a so-called STA PT1000. It's a smaller device which has an integrated furnace that is not optional, that cannot be exchanged. It's a fixed furnace. For the lower temperature range, it's the easy approach. Then we have the so-called basic unit, the STA PT1600 series, which is the most flexible, most modular setup. Here you can have any furnace attached to the system from the range liquid nitrogen temperature up to 2400. You can equip it with multiple gas controls. You can equip it with overpressure, with vacuum controllers, whatever. So this is the basic unit we are usually using. Besides that, we have special devices like the magnetic suspension balance, like high pressure versions. The magnetic suspension balance is a balance where you have a complete separated sample chamber. It's coupled to a balance by a magnetic levitating part. So you have a magnetic coupling that separates the furnace and the sample chamber completely physically from the environment, from the balance unit. So it's made for very critical conditions, for corrosive gases, for some critical atmospheres, like fluorine, like chlorine gas, or stuff like that. It's a TG-only system. There is an option to integrate a DTA, that's rather considered as a TG-only. And regarding the high-pressure versions, we have a HP1 and 2 system, which is a big floor-mounted reactor that can go up to 300 bars for bigger volumes for TGDC of anything. These kind of instruments are used for coal gasifications, for catalytic investigations, for very complex setups, and they are always custom designed and not from the shelf. And then we have a smaller pressure version that goes up to 150 bars. It's a tabletop instrument. It's a modification of the STA PD1600 that has a furnace, as said, up to 150 bars, up to 1000 degrees. So we are limited by temperature here. And this one is the tabletop version of our pressure balance, and it's also usually custom designed and not off the shelf. So that's the range. And as said, today's topic is more or less focusing on the new PT1600 platform. Regarding the hardware options of our STA PT1600 series, there are multiple optional options you can select. As I just mentioned, we can modify it to a certain degree. We have the option for a sample robot. We have, of course, vacuum options, including turbomolecular pumps reaching vacuum levels up to 10-6 millibars. You can add water vapor generators for controlled humidity, controlled water vapor atmospheres. We have completely free design gas dosing systems, so you can add as many gases, controlled gases by mass flow controllers as you want. From inert to oxidized reactive atmosphere, anything is possible. As that is design that's possible. And we can couple the instrument to improved gas analysis, which means we can couple FTIR, MS, and GCMS directly to the system, where we can analyze the outgassings and whatever comes off of your sample. Further options is the furnace program here. As you see, as I mentioned, we can cover a complete range, but not in one run. That's what I have to mention. We have furnaces from liquid nitrogen temperatures up to 2400. It's written -150 here instead of liquid nitrogen temperature, which is -196. The reason is down to -150 centigrades, we can control the furnace properly. If you want to go lower than that, you have just manually to open the cooling and make full liquid nitrogen cooling, and then start heating at -196, but you cannot do controlled cooling down there, just because this question sometimes pops up. And as said, we have liquid nitrogen cooled furnaces from low temperature range, and then from ambient temperature, we can go up to 2400. The design of the furnace, the used heaters, and also the used thermocouples for the desired temperature range define what atmospheres you can use. To make it short, up to 1600 centigrades, you can almost use any atmosphere. If you want to go higher than 1600, it gets more complex, and at a certain point, at roughly 2000 centigrades, it's only possible to use inert atmospheres or reducing atmospheres, but nothing else anymore. So oxygen or air is limited at roughly 1800 to 2000 centigrades with our furnace program. Higher than that, you can only operate in inert environment or reducing environment, depending on the furnace type. So that's the furnace program. And as said, we have water vapor furnaces, and we also have some special furnaces like infrared furnace heaters or light furnace heaters, which is also customized and which is available on demand. Regarding the sensor heads themselves, our STA is also quite flexible. For the TG-DSC, for the combination, we have the classic DSC heat flux sensor, which is the classic TG-DSC sensor, or crucibles. One is the reference, one is the sample crucible. Usually the reference is empty. In the sample crucible, you put your sample, and then the system measures both sides or both the temperature on both sides and automatically reads out the temperature difference as a thermal voltage, which is your signal for the DSC, and it measures the mass change. Besides that, we have a little bit bigger sensors, the so-called 3D KW type DSC sensors, which allows the use of bigger volumes. They consist also of 2 crucibles, however, not in this metal frame, but with multiple thermocouples that are put in a row at each side, at each crucible, to integrate the volume of the crucible properly and to measure DSC of bigger volumes. The typical DSC crucible is 0.14, 0.15 milliliters volume and is consisting of alumina or any metal like platinum, gold, stainless steel, something inert usually. And for the bigger 3D KW type sensor, we can use custom volumes up to roughly 0.7 milliliters. If you use the system in a TG only mode or also DTA mode, there are also DTA sensors. With the DTA sensors, there's also our new so-called 3-port sensor, which is a multiple thermocouple sensor, which is a higher resolution DTA. The difference between DTA and DSC is that the DTA allows bigger volume, but it does not allow to quantify the amount of heat flow. So you can still see if something is exothermic or endothermic. You can determine when it happens, but you cannot determine the amount of energy that's released or consumed anymore. So the DTA is a qualitative but not quantitative DSC technique. It's the older version of DSC, but it's still for some critical substances that are quite reactive, that would damage the sensor, or substances where you need more volume. The DTA is sometimes the better choice. And here, as I said, you're more flexible regarding crucible dimensions, and the crucibles can also be made of any kind of material. And besides that, you have the TG only mode. That means you can operate the system in TG only mode as well, where you have a TG sensor that ends up in a flat rod or in a rod with a little pin. Personally, I would prefer the pinned one. And here you put one of these crucibles on top, and then you just measure one temperature at the bottom of the crucible, which is the temperature of the sample usually, and only the mass changed. If you do that, you can use sample volumes up to 12 milliliters, so you can really measure a lot amount of sample, which is useful if you have very inhomogeneous material where only a very tiny amount of samples will react, or you expect just a tiny amount of samples to be reacting. And to monitor that properly, you can use very big volumes here. And besides that, we have special crucibles available as well, like a system where you can hang in something on a little wire if you want to put a foil in a gas flow, for instance, or you can have a mesh type crucible for better gas throughput. That brings me to the next topic. There's also our new, or one of our latest developments, our new forced flow design option. This new patent technology allows us to put the gas flow path directly through the pins of the capillaries and through the sample coming from the bottom of the crucible. So the gas comes through the pin where the crucible is mounted on and flows directly through the sample. That means you have more precise control of your reaction. You can monitor slow reaction rates and control your reaction rate properly. You can mix up your gases and your sample in a more ideal way, or in a more better and ideal way. You have real-time monitoring. You have easy adaptation to your reactions. In a typical standard design, the gas is released in the environment next to the sample using a separate capillary. And sometimes the sample gas is not passing the sample or the crucible in a way that the reaction can be monitored properly. That's why we developed this new design where the gas flows directly through the crucible and directly through the pin. Of course, the gas flow you can use is lower than if you just release it next to the system. However, you have a more proper control and you get a better reaction rate and a better understanding of your reaction rate. The drawing over here shows the gas path. So instead of a gas inlet at the side through MFC that goes into a capillary that's released next to the system, there is a split that directly goes through the system, is attached to the beam of the bar to not affect the mass change. So there is also a special design for the gas path to not affect the mass readout. And then it goes into the sensor and it goes within the sensor into the system directly into the crucible. which is a quite unique design and was a quite tricky development, but meanwhile it works quite well. So that's our latest and quite interesting option. This also shows a curve and a comparison to show you what's the difference. To understand this measurement, I have to explain. So you have a blue and an orange curve here that show the mass increase of a copper sample that was seeing oxygen. The brown signal is the oxygen that was, so the oxygen valve was opened here, then there was oxygen flow for a couple of minutes, and then the oxygen valve was closed. At that point, you see both curves, blue and orange one, show mass increase. The orange one shows a little bit faster mass increase than the blue one, and the reason is the orange one shows the forced flow technique. So here the oxygen directly was put through the crucible, while in the blue one, the standard default design was used where the oxygen was released next to the sample containing crucible. So you see the reaction rate of the orange one is faster, and there's a faster response, and the sample is reacting much faster and more completely than if you release the gas next to it. So that's just a test we did to show that the system really has a huge influence on the reaction rate and the reaction control of any sample. The blue line here, just by the way, shows the temperature. So we heated up to 750 degrees and then kept it constant for the experiment. But anyways, and as said, this is the oxidation of copper samples, and that was just done to prove that our system is working. Some further applications of STA besides this flow-through setup would be thermostability of materials like oxidation tests, oxidation induction time tests, which any DSC could do. You typically investigate composition of multi-component systems. You do tests for determining the grade of humidity, determine the amount of volatiles, the ash content, stuff like that. Furthermore, you can do melting and boiling point determination. You can investigate phase changes, anything a DST can do. You usually look at reactive atmospheres with TGA or STA. Sometimes you look at different atmospheres like sorption and desorption, reaction speeds, reaction rates, mass change due to reactions. That's what typically STA does. For many fields like polymers, inorganic materials, ceramics, food chemistry, pharma fields, life science, it's a quite flexible instrument at all. On the next slides, there are some typical applications. This one is the decomposition of rubber that was done. I show this in every STA presentation because it's a quite useful slide. What you see here is that the temperature was raised stepwise to 3 plateaus. After the first step, there's an initial mass loss. The orange curve shows you the mass loss again. So you see a loss of volatiles, you see a loss of humidity in the first segment in inert atmosphere. Then you have a second heating step where a lot of thermal decomposition takes place. So it's pyrolysis, oxygen-free decomposition, and any organic will be transformed into carbon at that point. And then the atmosphere is changed to oxygen finally, and there's a third heating. And during this third heating, all the organics burn off, so you can determine the amount of organics during the third heating segment. And the green curve again shows you the DSC signal. So during this decomposition reactions, you see big endothermic and exothermic peaks, giving you the amount of how much carbon is created, how much carbon is burned off, how much volatiles are released. So that's a typical experiment may look like. Just another example, it's the decomposition of calcium oxalate, which is a reference material we are usually using. That shows a 3-step thermal decomposition. First, in the first step, it loses its crystalline water. And then you have 2 more steps where it loses carbon monoxide and carbon dioxide. In that example here, you can see these brown lines additionally to the orange mass change and the green DSC curve. These brown lines here are showing you the readout of a mass spec. So the upper line here is the mass trace of water, where you can see there's a loss of water, a big peak at the first place, then a little bit water loss here, just a tiny amount that you almost cannot see. by TG directly, and that's it. The other ones are the loss of carbon monoxide. So this is the monitor of the mass of carbon monoxide. So you have a huge peak during the second step, which is the release of carbon monoxide. And the lower line here is carbon dioxide, where you see a low effect during the second decomposition step and a big dioxide at least. So that's how an experiment looks like if it's coupled to a mass spec. Yeah, I will not so much focus on the special instruments. As I said, we have inductive heaters, we have pressurized systems, we have a special design for glove boxes and hot cells where we can separate the electronics completely from the instrument. And for all these, special configurations, as said, there are also special, of course, applications, and also a lot of customization possible. As said, we can separate electronics. We can use inductive heaters or light furnace in case of a resistance furnace is too slow or has too slow cooling times, stuff like that. And we can do many options. But as I said, I will not focus on the special options now for the moment. Just one application to show. This is a sorption measurement and the pressure balance. So this is the sorption of hydrogen on a Titan surface at 700 centigrade isothermal segment. This experiment was carried out at different pressures, beginning at 10-3 millibars and then increasing the pressure step by step. So the experiment was performed at different pressure steps. And you can see here, at a certain pressure level, you reach a saturation. So already at 0.5 bars, you reach saturation. The amount of hydrogen that will be sorbed by the surface will not increase anymore, even if you go up to 5 bars. And such experiments or stuff like that helps you to find saturation levels and the maximum of possible sorbed hydrogen or any other gas on a sorbent that you can use. But as said, I will not focus that much on the special versions. I want to come back to the new design. As I mentioned before, today's topic should be more or less a repeat of the webinar we started the year with in January. In January, we promised that by April we will launch our new design, and we did so. Meanwhile, our STA PT1600 series looks like this. It's no longer the blue and white system you may know. It's now this new black design. That's, of course, not only a design and a little nice new panel with some nice fancy LEDs. It comes also with some new features and functions. The most obvious first, it has a completely new touch panel with much more user-friendly functions than the old one. The old one was just monitoring the active curve, and that's it. The new one can be used to really control the system a little bit more. You have a completely integrated toolkit panel, so there's integrated storage place where you can find tweezers, replacement sensors, and stuff like that. You have a much smoother and much more improved furnace lift. You will see once you have it in your fingers or you visit us at one of our exhibitions. You have a complete new structured software package, which is the more important thing. And we have now intelligent systems. Finally, we can now say, okay, any configuration of the system will automatically be recognized by software, and you do not have to select anything by yourself. That's one of the biggest improvements, in my opinion. In detail. Let's start with the software. We did a lot of software improvements with our new version software. We have now a LexBus system for plug and play, which I just mentioned. It causes direct communication within our system. That means new hardware parts like additional furnaces, different furnaces, sensors, sensor configurations, additional gas panels and stuff like that will automatically be recognized by the software. It will automatically be configured by the system, and you do not have to do it by hand anymore. We improved our furnace and oven control, which means you have a much more precise temperature control. We improved our controllers. You have lower delays and lower overshoots in the temperature profile meanwhile, which is also a big improvement. We also completely redid our interface. So our user interface has a new design. It's a little bit more easy to use. There are lower amount of icons and there are some functions that were never used or that were not very useful and obvious to the customer were removed and hidden, partially hidden, partially removed, which is also a nice improvement for the user. What's also new, we can now bring in complete process security. The data is protected at all times. It's in a fail-safe manner. That means the data is always copied in a database, but also saved. In case of the system fails or there is a power interruption, stuff like that, the data is safe. The data is automatically located in a safe place and not abandoned and not aborted. So if a run is aborted due to power failure or anything, the data to that point will be stored and you can access it later. We have an automatic error and bug fix system, so it detects errors automatically and will document them and try to fix them by itself, and automatically will try to report it to our developers if you have internet access allowed, which minimizes downtimes. You will also get automatic updates of our software now. In the past, you would have to request them. Now, if you allow that, like a Windows update, if you allow internet connections, the system will update automatically, and you will also get new features. Some features, some functions will pop up in the future. And if a customer comes and wants a certain evaluation function and we integrate that to our future software, you can upgrade that in your version. We have a permanent system monitoring, which means our software automatically monitors the parameters. And if anything is not working properly, it can automatically give the user, and if we are connected, also us, a little error hint that the maintenance or service visit would be necessary. After all, that optimizes the maintenance and detects problems before they can cause damage, and in ideal case before they occur. And that's our new software approach we have with the new system. There's also one thing we introduced here, which we have to see how it's accepted by users. We have a Linseis direct lab link, which means if you set up an experiment and you feel unsure or you need help, you can directly access a chat function with our experts here in-house during the experiment, or if you're sitting in front of the instrument, you can use the online chat function directly and get in touch with us when you do the experiment, so we can help you, guide you through the process. And that's also for the user, it's quite comfortable. I have to see how they accept it and how fast we can respond here. We also modified the electronics. We optimized our baseline width. We optimized our accuracy and also reproducibility by a new digital electronic that is state of the art and is, of course, also a little step forward. And finally, we have some hardware features. We did improvement of the design. You already saw it. It looks much more worthy than the old one. It has some new features, a new touch panel, and we have a lot of new hardware features like the tree-couple high-resolution DTA setup, like completely jacketed sensors. We did not have them in the past. Now we have them, so we have complete jacketed DTA sensors for very corrosive atmospheres, and we have the new patented forced flow method that I just introduced to you. So that's what we did hardware-wise. So these are the basic new features of our new instrument. And that's also the end of this presentation here. As said, it's more or less a repeat of the STA introduction by the beginning of the year. And now as we meanwhile successfully launched the new design to the market, we can also present the new features.